Alright, in this one I'm going to go through mutual induction. And mutual induction is when you use a changing magnetic flux in one coil to cause a voltage in a second coil. A bit like we did in our earlier demonstration back here. So we changed the flux in this primary coil, coil 1, and it induced an EMF in the secondary coil. So we'll have a look at how that works. So an electric toothbrush, for example, in fact I will do this. So an electric toothbrush has a primary coil in the charger that kind of sits on your sink, and it has an alternating current in it. And that alternating current creates a constantly changing flux. Alternating current just means the current is going first in one direction and then in another direction, and it changes all the time. So the flux is always changing, because the bit that's pointing upwards is going to be a north pole and then a south pole and then a north pole. The secondary coil in the brush handle will experience a flux change. EMF induced and battery recharged, like we saw with the car or the artificial heart in the previous video. Okay, so if you can charge your 4-volt cell phone battery from the main supply by plugging in your charger, which seems a bit weird because your cell phone is designed to run at 4 volts, but we're supplying an enormous voltage, 60 times bigger. And so the answer to how we can charge it is we step down the voltage using a transformer. Okay, so we have two types of transformers. We can either have a step down, which reduces the voltage, and we can use them to reduce the voltage to low voltage devices like phones or computers. Can operate off the mains. Or we have step up transformers, which increase the voltage. And there are many devices where you need a big voltage, like old-fashioned TVs needed a really big voltage to accelerate the electrons in the cathode ray tube. And there are many devices now as well. I'm sure you've seen on the back of some devices, do not open high voltage. And that's because there'll be a step-up transformer that steps up the voltage to something really high. I think microwaves have those as well. Okay, so how transformers work is that we have an alternating current here to a primary coil, and which causes a changing magnetic field in this iron core. That magnetic field produces a changing flux in the secondary coil, which induces an EMF in the secondary, which can be used to drive a current through the secondary. And because we have different numbers of coils here, we're able to change a small voltage to a big one, or vice versa. So an alternating voltage across the primary coil causes an alternating current in the primary coil, and this produces an alternating magnetic field in the iron core, and this produces a continuous flux change in the secondary coil, and this produces an induced voltage, or EMF, in the secondary coil. And the output voltage depends on the input voltage and the ratio of the turns. So basically, if we have more turns in the secondary than in the primary, we're going to get more voltage in the secondary than the primary. And if we have 100 times more in the secondary than the primary, then we'll step up the voltage by 100 times. Okay, so if the secondary number of turns is bigger than the primary, this is a step up transformer and the output voltage is bigger. If the secondary number of turns is smaller than the primary, then this is a step down transformer and the output voltage is smaller. In theory, the energy output equals the energy input, but in practice, some energy is converted to heat. And it's due to two main things. The first one is that we lose some energy in the coils, and you can reduce that by making the wire out of good conducting material, so like copper, or a good conductor. The second thing that causes energy losses are eddy currents in the iron core, which is basically, because the iron is also a conductor, a changing magnetic field causes the electrons in the iron to swirl around, and those swirling electrons in the iron causes the iron to heat up. And that's also wasted energy that we don't get out on the other side. And so we can reduce that by making the core out of many thin insulated sheets of iron. So you kind of make lots of flat sheets of iron and you put insulating glue in between to stick them together. That kind of prevents the electrons from swirling around too much inside the iron. So in an ideal transformer, the power in is equal to the power out. So the voltage in the primary times the current in the primary is equal to the voltage in the secondary times the current in the secondary. Okay, so we'll look at these problems. So Anna suggests that if a transformer can increase the voltage, you can get more energy out than you put in. If you look at this equation above, we see that's not really true, because if the voltage is stepped up, the current we get out is much smaller. So that even ideally, E out equals E in. So energy out equals energy in. In reality, of course, the energy that we get out will be less because we lose some as heat, as mentioned before. Cheryl wants to make a transformer to charge her cell phone from two 40-volt mains. The cell phone battery is 4 volts. So you want to find out what NP over NS is. So we know that Vs over Vp is equal to 4 over 240, which is equal to N, well, the turns ratio is 4 over 240, or 1 over 60. A cell phone battery draws 100 milliamps. What current flows into the primary coil? So we know that VPIP equals VSIS. So IP is equal to VSIS over VP, which is equal to, the secondary voltage is 4, the secondary current is 100 milliamps, divided by the primary voltage, which is 240. So we can plug that into our calculator. So 4 times 100 times 10 to the negative 3 divided by 240 is 1.7 times 10 to the negative 3. 1.7 milliamps. The primary coil has 300 turns. How many turns on the secondary? Well, we know that NP over NS is equal to 1 over 60. So NS is going to be equal to 60 hold on a second. Here we've worked out the opposite. So this is actually ns over np. So this is actually, so this is 4 ns over np. So np over ns is equal to 60. So np over ns is actually equal to 60. So 60 is equal to 300 over ns. So ns is equal to 300 over 60, which is equal to 55 turns. Okay. So these transformers are particularly useful in transmitting energy over long distances, because if we step up the voltage to something really, really high, then the current is going to drop, as we saw from this equation. And with a low current, we're going to generate less heat in the transmission lines. So if we send the voltage through the transmission lines, send the energy through the transmission lines at a very high voltage, we're going to lose much less energy as heat in the cables. So to reduce power loss, the resistance is firstly made as small as possible, is made as small as possible. And to make the current in the transmission line small, the voltage is also stepped up to around 500,000 volts, and therefore we reduce the current and we reduce the power loss. At the other end, a substation transformer steps down the voltage to about 3,000 volts, and that's sent around the streets. And then local transformers, like the one in the picture here, that steps the voltage down to 240 volts, which is what we get into our houses. So here's an example. A transmission line has a resistance of 5 ohms, and you want to transmit 1,000 watts of power. You could do this either using a high voltage or a low voltage. We'll see which wastes the most power. So the power loss using a 1,000 volts and 1 amp, so the power is equal to I squared R, which is equal to, well, 1 squared times the resistance, and we're told that the resistance is 5 ohms. So 1 squared times 5 is equal to 5 watts. If we use 100 volts and 10 amps, then we're going to get 10 squared times R, which is 100 times 5, which is 500 watts. So we can see that by stepping it up tenfold, we save 100 times the energy per second. So bigger voltage and smaller current leads to much less energy wasted in the transmission lines.